Swayam Prabha. Digital India. Educated India.
Welcome back to the course Mechanics of Solids. So, in the last lecture we are discussing about the stress strain relation. So, we have seen a few definitions, okay, and few terms which will define the stress strain behavior of a particular material, right. Now, we are going to discuss today this elastic stress strain relation, okay. So, now we are going to deal only with, because in this particular course we are not going to discuss any other type of material. We are going to discuss only about isotropic material. Now, what is that? The definition of isotropic material: one whose elastic properties are independent of orientation, okay. So, the what is isotropic material? Isotropic material is one whose elastic properties are independent of orientation. Suppose you are considering one body, okay. So, the body is having some say elastic properties in x direction, y direction and z direction, right. Now, if you rotate the body, okay, so that rotation will not cause any difference in the elastic properties, right. Now, what are those elastic properties? We are coming to that point. So, mostly you know already we have talked about that thing, modulus of elasticity, right, E value, E, right, earlier when we are discussing about the load deformation characteristics. Anyway, so that is one of the elastic property, right, the modulus of elasticity or the Young's modulus, you know from your physics. Then another property is the Poisson ratio, that will give you the relation between the lateral strain and the longitudinal strain, right. So, these are all elastic properties. So, if you rotate the body in any direction, that elastic properties will be remaining unchanged. So, that kind of material is known as isotropic material, okay, fine. So, now here at this point, before establishing the relation between stress and strain, we should know that if I apply normal stress, does it cause any shear strain or not, or if I apply shear stress, does it cause any normal strain or not. What does it mean? So, suppose I am saying that if I apply normal stress, only normal strain will happen, and if I apply shear stress, only shear strain will happen, okay. So, that is a proposal I am making, but we can prove it that normal stress only causes normal strain, no shear strain will be caused by the normal stress. Similarly, shear stress only develop shear strain, not the normal strain, okay. Now, let us look at this figure, okay. So, we can prove it actually. So, what is this in this figure? So, we are saying, well, so if I apply normal stress, so sigma x I am applying on this body, okay, that normal stress is causing some shear strain, and that is shown by this dotted line, okay. So, that means you are getting some angular distortion, okay. What I am saying, that due to the application of sigma x, I am getting some amount of shear strain, and that is shown by this dotted line, fine, there is no point no ambiguity in that. Now, what I am doing, I am just rotating this x axis by an angle 180 degree. I am giving some 180 degree rotation, and with that 180 degree rotation, this body will take the configuration of this body. So, sigma x, direction of sigma x remains unchanged, there is no problem at all. Only thing is that now you are getting the angular distortion in this direction. So, if I say this is the direction of your angular distortion, that means the shear strain is happening in that direction. Okay? Shear strain is nothing but your angular distortion. Okay. Now, if you compare with this figure and this figure, what you are getting? You are just rotating the axis, nothing else. You are not changing the stress, you are not changing the material, no change anything, anywhere, in this configuration, right. Only change you are making, that is, you are giving some 180 degree rotation to the x axis, that is all. So, with that 180 degree rotation, you are getting the shear strain in opposite sense. So, in this figure your shear strain was in this direction, right, but in this figure you are getting shear stress in this direction. That means, the angular distortion is happening in the reverse direction. So, you are getting just opposite sense of shear strain, but as long as you are dealing with isotropic material, the rotation should not change the elastic properties, right. So, therefore, this sigma, due to the application of sigma x, when you are applying some rotation, you are getting the change in sense of shear strain. If you say this shear strain is positive, then in the other figure you are getting shear strain is as negative. That is completely contradictory statement or the contradictory findings, right. So, that should not happen as long as you are dealing with isotropic material. Therefore, only thing is possible, at this stage, only the possible thing is that this normal stress should not create any shear strain. If it creates shear strain, then basically you are getting this kind of ambiguity, but to avoid this ambiguity, only you can say the normal stress does not create or cause any shear strain. That is the only possible thing to satisfy this isotropic material. Similarly, for other kind of shear strains, so if this shear strain whatever you are seeing, other two components of shear strain can be nullified or can be said that they cannot be developed due to the application of this sigma x, right. So, in that way we can say normal stress only produces normal strain, okay. That is the thing we can conclude, that normal stress only produces normal strain. Similarly, we can prove that proof I am not showing. Similarly, we can prove that shear stress only produces shear strain. So, shear stress does not produce normal strain. Similarly, normal stress does not produce shear strain. Okay, fair enough. So, with that proof or with that discussion, now we can discuss or we can establish the relation between the stress and strain. Okay. Now, let us talk about this epsilon x. So, epsilon x and the relation between epsilon x and sigma x, as you know from your previous discussion in some physics book or physics mechanics part of the physics, that the normal strain along x direction is related to the normal stress along x direction in this equation or in this fashion, correct. Okay. Similarly, I can get epsilon y is equal to epsilon z is nu times epsilon x, which is nothing but nu times sigma x by E, where nu is nothing but your Poisson's ratio, you know that, right. If you pull the body, the other two directions will be contracted. That is the common thing we generally observe, and that has been observed by most of the materials, and that can be written like that. Okay. This negative sign is because of that, because if you are getting elongation in the x direction, in y and z direction you will be getting the contraction, and that contraction is defined by this Poisson ratio, right. Similarly, I can write epsilon y is equal to sigma y by E, and epsilon x epsilon z equal to nu into epsilon y is equal to nu into sigma y by E. In this case only sigma x is applied. Okay. So, if you consider a body, only sigma x is applied, and due to that you are getting this relation. Similarly, in this case basically only sigma y is applied, okay, and because of that you are getting the strain components. And likewise you will be getting when only sigma z is applied, so you will be getting this, you know that. Okay, fair enough. So, normal stress only produces normal strain, no shear strain. You see here, the normal stress sigma x or sigma y or sigma z only produces normal strain epsilon y, and due to the Poisson's effect you are getting other two normal strains. Fine. Now, for shear strain, okay, you will be getting say gamma zx. So, this is the shear strain in zx plane that is caused by shear stress and one modulus, and that modulus is known as shear modulus. So, G is known as shear modulus. Okay. And later on we will see that this shear modulus is not an independent say parameter, it is dependent on E and nu. So, the independent parameters are only two, E and nu. E is the elastic modulus and nu is the Poisson ratio. So, you can express G, that is the shear modulus, in terms of E and nu, that we will see later on. Okay. Similarly, if you have gamma xy, that is given by tau xy by G, and gamma yz, that is tau yz by G. Okay. So, now if you write down all the strain components, the relation between strain and stress, then they will be looking like this. So, epsilon x is given by 1 by E sigma x minus nu into sigma y plus sigma z, okay. Epsilon y is equal to 1 by E sigma y minus nu into sigma x plus sigma z, epsilon z equal to 1 by E sigma z minus nu into sigma x plus sigma y, and gamma xy equal to tau xy by G, gamma yz equal to tau yz by G, and gamma zx equal to tau zx by G. So, this is nothing but your, as you know, generalized Hooke's law. Okay. This is very, very important as long as we are discussing about the elastic relation, elastic stress strain relation, though the plastic stress strain relation is not included in your syllabus. So, this is your elastic stress strain relation, and of course, the linear behavior we are considering, isotropic material we are considering. So, if you know the stress components, okay, sigma x, sigma y, sigma z, and tau x y, tau y z, tau z x, you can find out the strain components, or rather if you measure the strain components, because you cannot measure the stress. So, if you measure the strain components, then from these equations you can find out the stress components. Okay. Now, as I was saying that this G value is not an independent parameter. Okay. This G is not an independent parameter. So, G is dependent on E, and it can be proved that. Okay. However, this proof I am not showing. It can be proved that G equal to, for the proof any classical say mechanics book you can refer. However, I am not showing that proof here. It can be proved that is G equal to E by twice of one plus E. Okay. So, G is dependent on E and nu. So, the basic parameters are two, that is E and nu. Okay. So, once you know E and nu, you can find out G. So, once you know G, you can establish this relation, okay, shear stress versus shear strain. Okay, fine. Now, we will come to thermal strain. Now, we will come to thermal strain. Now, what does it mean? Suppose if you consider any body, any material, any system, okay. So, if that material is under some temperature, and if you raise the temperature to certain extent, right. So, due to that increase in temperature, you will be getting some deformation developed in the material, right, that you know from your thermal expansion coefficient and all those discussion. Okay. And as long as your material is behaving as elastic, that means if you release or if you decrease the temperature from that point to the original temperature, then again that much of strain will be disappeared, or that is, so that kind of strain will be participating, or that kind of strain will be the extra strain, okay, on top of this mechanical strain. So, these are all mechanical strain, right, epsilon x, epsilon y and gamma x y due to the application of stress. So, these on top of this mechanical strain, due to the temperature rise or temperature fall, you will be getting the thermal strain, and that thermal strain will be additive or subtractive due to, I mean if you increase the temperature or if you decrease the temperature. Okay. So, now we should know how we can calculate this thermal strain and how we can couple the thermal strain and the mechanical strain. Okay. So, suppose as we know from our discussion from the physics, so this is a say any material, so this is a bar of length L, and due to the temperature rise, this much of length is getting increased, say delta L. So, initial temperature say T naught and final temperature say T, then I can write delta L, okay, from the physics, L into alpha into T minus T naught, where alpha is nothing but coefficient of linear expansion, linear or thermal, sometimes we say thermal also, okay, coefficient of thermal expansion, fine. So, if you know, I mean it depends on the material, if you use steel, if you use copper, if you use aluminum, depending on that alpha value will be differing, and that you will be getting from any standard book. So, if you know the initial temperature and final temperatures, that means the delta T basically the temperature difference, if you know, okay, you can find out how much difference in length or how much elongation is happening. Okay. It could be elongation, it could be contraction depending on the temperature rise or fall. Okay. Now, I mean based on that your thermal strain can be calculated as your thermal strain can be calculated as epsilon x due to thermal T, and they will be same. Okay. Epsilon y epsilon z is equal to delta L by L, where delta L is here. So, it is simply alpha into T minus T naught. But you should remember, because the temperature is uniformly increasing in the system, you are not increasing the temperature for one part of the system, another part is not experiencing the temperature rise or fall, right. So, you are globally or overall temperature rise is happening. So, your shear strain must be 0. Right, only you will be getting normal strain due to the temperature rise. So, therefore, the total strain equal to strain due to stress, that is a mechanical strain you can say, plus strain due to temperature. That is your total strain. If I say what is the total strain? So, total strain will be the mechanical strain plus temperature strain. Okay. So, that is expressed as epsilon, that is the total strain is equal to epsilon E plus epsilon T. So, that is coming from your stress part and that is coming from your temperature part. Okay. So, whenever we, I mean this will give you, so unless until it is mentioned, I mean if it is mentioned then fine, otherwise you can consider only the mechanical strain. But the idea is that for a system the total strain depends on, of course the material is behaving still in the elastic limit, the total strain is dependent on the strain due to stress, that is the mechanical strain, and strain due to temperature, that is thermal strain. So, I will stop here today. So, we will continue in the next class with general state of, I mean general equations of general state of stress, right. I mean the equilibrium equations for general state of stress. So, that thing or the general equations of the elasticity, that will be discussed in the next class, and then we will be discussing about the failure criteria. So, thank you very much. I will stop here today.